So we are now going to hear our last talk before the lunch break, and this is going to be from Rob Habermeier, and he's going to be giving a talk on Substrate, and specifically what he's been working on lately. So Rob's the co-founder of Polkadot. He does a lot of the implementation of like the grandpa consensus algorithm, which some people presented here, which is the novel consensus algorithm for Polkadot, and then also making that consensus algorithm into a substrate runtime module so that anyone who's building a chain can use it. So he's going to be talking about some of that work and a bunch of other stuff that I don't even know about yet. So give it up for Rob.
Thanks, Jack. Hello, everyone. Is there a clicker? Yes, here it is. I've been doing a lot of the implementation stuff for Polkadot, and that spans quite a range of projects at this point. So there's the Grandpa consensus implementation. I won't be talking about that today, but on the 7th, on Thursday, I have a big talk where I'm going to dive super deep into all the consensus stuff in Polkadot, but that's its own talk. So what this one is about Substrate. We at Parity Technologies, we built this framework called Substrate. It's for building blockchains, basically making that whole process easier. This talk is focused on sort of an extension to Substrate called Cumulus. It's some libraries for writing runtimes and integrating with Polkadot, basically to write parachains with Substrate. So Polkadot, first of all, I guess I'll start with a quick introduction to what Polkadot is. So Polkadot is it's a network of heterogeneous chains. You have chains that do different specialized things that are all secured under one consensus mechanism by the same group of validators. They can pass messages amongst themselves, and it's governable, it's extensible, and it aims to be scalable as well. So one of the core philosophies that we've had is this idea that specialization breeds optimization. The idea is that if you have to meter for very fine-grained units of computation, things like add a number, multiply a number, shift left, shift right, then you have to stop after each of these small operations and subtract a gas fee, essentially. So this gets very hard if you've tried to do things like implement complex cryptographic primitives or just particularly complex calls. So if you have a rough idea of what your chain needs to do, things like, for example, file storage or some specific kind of zero-knowledge proving, you can package that up into a much coarser-grained operation and only bill fees for each of those. And that's basically what I mean by specialization breeds optimization. When you specialize into a specific type of transaction, you can optimize the implementation and, as a result, do more computation. So what a blockchain is composed of, I like to think about this. This is not 100% accurate because there is some cross-feed between them, but I like to think of it as a separation between the consensus algorithm, so some kind of process that's providing security on the blockchain. There are some blocks being created, it doesn't really matter what's in them, and there's consensus over that. So everybody eventually can come to an agreement which is secured economically that things are finalized. So that's what consensus is. And then there's a state machine. So state machine being what do those transactions do? What's actually inside the block? What kind of computation is happening? It could be UTXOs, it could be EVM, it could be WASM, it doesn't really matter. This is what we package up into that state machine abstraction. So what we try to do with Polkadot is sort of separate those abstractions. Basically, when you're building a blockchain, if you have an idea for a blockchain, most likely the main thing that you're trying to do is you've come up with a unique state machine, some kind of unique form of transaction that's actually the novel part. Consensus is often not innovated on, and speaking as somebody who's actually implemented a number of BFT consensus algorithms, it's actually really hard, and it's a lot of development work. So the fact that you can ignore building consensus algorithms, you know that the security is provided from another level. That's very, very valuable. It means that you can spend all your time focusing on building that state machine. So at a 10,000-foot view, the way that this works is we have something called the relay chain at the top level. So the relay chain is the main chain of Polkadot, where you have validators and staking and governance going on. And this is where parachains are registered. So parachains are essentially just pieces of WebAssembly code. I'm going to get into that in a moment, which tell you how to validate the blocks. So the blocks from Polkadot's perspective are just raw bytes. And these parachains are distinct, specialized, heterogeneous state machines. And one form of parachain, which I'm not going to talk about in this talk because they're sort of a whole different breed, is bridges. So what I'm going to talk about is what you would call maybe more native parachains, parachains that have Polkadot do all of their consensus and computation for them. What a bridge is something distinct where you actually have another chain which has its own consensus process, does its own computational work, and that those proofs of finality of that other chain are bridged over to Polkadot and vice versa. So that's sort of a different matter. So I won't be talking about that today. So the anatomy of a parachain, let's go into basically what a parachain is. But this talk, I'd like to aim more at developers. So this is not just a high-level view of, okay, this is what the abstraction is. It's really more meant to be, this is what the abstraction is, but also how you apply it to your own work when you're writing that code. So the biggest part is this validation function that I mentioned before. It's a piece of WebAssembly code. Validators don't know any parachain-specific logic beyond what is encoded in this validation function. So that's WebAssembly code that has a signature that looks like this. That's sort of pseudo-Rust, but I'll walk through it. So we have this function validate. We have the last header. From Polkadot's perspective, that's just some bytes. Right, so that ampersand brackets U8, that just means some bytes. We have some information about the state of the Polkadot relay chain. So that would be maybe the last block header that's in Polkadot, the last Polkadot block header, not the Parachain block header, and the incoming messages to that parachain. So this is a state that's actually changing for every relay chain block. This does mean that parachain blocks are localized to relay chain blocks. So if you would submit a parachain candidate, and it was not included, you would not be able to submit that exact same parachain candidate to the next relay chain block when that consensus process happens. So it's sort of a one-off thing. Either it gets in or it doesn't. And then the last part is this block data. So this is meant to be, it's something like a proof of validity. It's not just the block body, it's not just transactions, it's something more than that. And I'll revisit that once I've set the ground for an example. The other half of writing a parachain is to write the collator node. So writing the validation function is actually relatively easy because it's just a piece of deterministic code, pure function. It takes some inputs and it gives an output. Either it's yes, here's the new block header, or no, that input was garbage. So that's pretty easy to write if you have the right tools. The harder part is maybe writing the collator node because you have to do things like gossip transactions. You have to come up, what a collator node is supposed to do is come up with the inputs to that validation function, the block data specifically, such that that validation function returns true. So it has to have the logic for actually handling those messages that are incoming to the parachain. It has to have that logic for actually propagating parachain blocks to other nodes in that parachain's network. Now, you don't necessarily need those things because as it happens, parachains don't actually have to be blockchains. But within Substrate, they are. Like, you can write specialized parachains that actually aren't blockchains at all, and then this sort of doesn't really apply. Like, for example, if you would have a federated parachain where it's just, actually, here's just Bank of America issuing blocks to Polkadot, and they have their own private thing attached to it. They wouldn't need to go through all this hassle. But if you're writing a decentralized parachain using Substrate or some other framework, writing the collator node is actually quite difficult. So the remainder of this talk is really going to be going into how do we make that difficult task of writing a collator node much easier. So parachains are simple abstraction, but like all blockchains, are pretty complicated to implement. So I put together like a very short list of some of the things that you have to do when you're writing a blockchain. So consensus algorithm, database, RPCs, that sort of thing. A lot of optimization goes in there. This is just a very short list that I made for you guys. We basically have done that before at Parity. We've done that a few times. We wrote an Ethereum client, which I'm sure many of you have at least tried out. We wrote Bitcoin client. We're writing the Zcash one right now. We've written the Polkadot node as well. So basically, we've done all this before, and we figured, well, okay, we've done it all before. We know how all that works. Why don't we just package that up into a set of tools? And we've been talking about that probably for the last 6 or 8 months more intensely, but we started work on it about a year ago, and that was called Parity Substrate. So it's just a set of tools for writing blockchains. But critically, the blockchains that we've supported thus far have been what I would call sovereign chains. So there's a framework for pluggable consensus and things like that, but it's been, as of yet, more focused for writing chains that are freestanding, that provide their own consensus and finality and aren't networked with other chains as part of their first-class validation. So among other things, Substrate does provide this framework for pluggable consensus and some, I guess, what I would call composable runtime modules. So when I talked about the state transition before, the way that you do that in Substrate is to write what we call a runtime. So a runtime is essentially made of specific components that define transaction types and call types and ways that you can interact with the chain. And these are actually just modules that you could write yourself or put together from repositories that others have published on GitHub. There's a set of modules that we've put together called the SRML, the Substrate Runtime Module Library. But of course, you can write your own as well. So typically a chain that you write with Substrate looks something like pre-built components for things like balances and transfers, perhaps staking and governance, combined with those special bits that make your state transition novel, whatever your research team has come up with that nobody else has. So what Cumulus is an instantiation of that pluggable consensus framework to provide Polkadot consensus. So it's an instantiation of pluggable consensus that follows the relay chain. It knows how to actually run another blockchain. Sorry about that. It knows how to run another blockchain node internally, which is typically a light client, and follow the relay chain. The other thing that Cumulus provides is essentially a way of extending without substantial modifications, actually with quite minimal modifications, extending the Substrate runtime you've already written into a Polkadot validation function compatible runtime. Because typical block authorship and typical block execution have some key differences to the validation of Polkadot parachains. I feel like this clicker is not working. I'm going old school. So Cumulus is meant to turn an already written Substrate chain. That's sort of our idea, right? Because obviously we've put Substrate out there, and a lot of people have been using it already, have been building on top of it. So it would be kind of crazy if we would just put out these new libraries and say, okay, you have to rewrite everything. Everything you did before is gone. So we're not doing that. Instead, essentially, you just add an extra module, an extra piece of functionality to your runtime, and then it can become compatible with the Polkadot relay chain. So a node using Cumulus, as I said before, embeds a Polkadot Lite client. This is so that it can follow the consensus and finality of the relay chain. So that's sort of what you would have to do, I guess, if you think about any sharded or partitioned blockchain system, is that when you have these root chains from which you're drawing security, you have to essentially run one extra or maybe multiple extra nodes so that you can actually process that consensus. So nothing I say after this point applies to bridge chains. If you would write, for example, a Bitcoin or Ethereum bridge, it doesn't really fall into these categories. This is strictly for writing native parachains. Right. So how do parachains differ from sovereign chain substrate? I'm sure you guys are asking this question because I've sort of led up to it. So the part one is block authorship. So parachains draw their finality and consensus from the relay chain, whereas sovereign chains are providing their own finality and consensus. So this can be done in a number of ways for a sovereign chain. You can have agreement over every single block, a la PBFT. You can have something like Albatross with Reto, which was just mentioning, where you have more progressive consensus. You can have Grandpa, which we've designed and implemented, which is sort of a chain-based consensus system where you're voting on chains in a PBFT-style round and a common denominator is selected. But in parachain consensus, you really only have one other option, which is to follow whatever the relay chain is doing. The relay chain, in fact, does use Grandpa. And block authorship in the parachain space depends on information derived from the relay chain. For instance, whatever the block hash of the best relay chain block was, whatever the messages coming from other parachains are, whereas block authorship on a sovereign chain is completely isolated, so you don't have to worry about this stuff. And these two factors actually add quite a substantial amount of computation. So revisiting this function, right? So we have this validate function that we need to come up with a way, that's what block authorship is in the context of a parachain. We need to come up with block data that fulfills the requirements of this function such that this function returns okay with the new header. So Polkadot's block data is just meant to be some kind of proof. It's supposed to maybe include transactions, some subset of the state. It could be a zero-knowledge proof. The WASM validation function doesn't really care. But as an example, this is how Substrate structures things for now. So we have the state organized into a tree. There's a root stored in the header. It's just as Ethereum does it. So, I mean, for what you're really doing is transforming a light client into a deterministic small piece of code that's compiled down to WebAssembly. So when you would write an Ethereum light client, you would do the same thing. If you want to prove a transaction's execution on Ethereum, you would get the header where that block was executed. You would check what that state root is, and then you would request all of the tree nodes necessary to execute that transaction. The tree nodes encode different pieces of account state. For example, if I want to read account X, I go down into the leaf where the key is X. And I read out the account state, and then I can start to work with that. So Substrate has a similar model for state, although it's not account-based, because it's a bit more abstracted than that. You could write something that's account-based, but the way that it actually works is that it's just key-value-based. So you have arbitrary keys, which are bytes, mapping to arbitrary values, which are also bytes. So let's say if we would have one transaction, the yellow transaction, and it needs these tree nodes to execute. And then we would have this blue transaction, which needs these other tree nodes to execute. What we would want to pass to this validation function is just these tree nodes. So, I mean, in practice, this tree is humongous, right? The tree node sizes, all in all, add up to gigabytes and gigabytes and gigabytes, and we have huge problems with that, with state bloat. People are talking about storage rent and ways to clear this out, and how to make it not so massive. So, of course, you want to omit all of those parts which you aren't using. So what a block data proof for a typical substrate chain would look like is just this subset of all tree nodes which you need to execute the block transactions. So what Cumulus collator does is exactly that. So this is essentially the pre-built binary, which is generic over a substrate chain that's been tweaked with Cumulus runtime. So that's a binary that you can deploy, which just knows how to build WASM validation functions, and it knows how to build the block data that satisfies them. And the pipeline for doing that is something like this. So we're essentially combining two big pieces of information. So one of those pieces of information is the state of the relay chain, right? So we're watching the relay chain, we're seeing what's the latest head of the relay chain according to our fork choice rule, what messages are incoming from other parachains, we're fetching those from our other peers. We have that data. On the other side, we have the transactions data for our parachain. So we have some kind of queuing, gossiping, collation happening where we're observing which transactions are coming in from our other peers on the Parachains subnetwork. So we want to combine these two pieces of information, come up with all of the state tree nodes which are necessary to execute those incoming messages, which it's up to the parachain really to decide how those are executed. They could be perceived as just regular transactions. They could be perceived as some other kinds of operations entirely. So we need to figure out which state tree nodes are necessary to execute those incoming messages, and we need to know how to execute those incoming transactions. So the way that we do this in Substrate is we have this special Polkadot inherent data that's passed to the Substrate runtime. So we execute this special inherent transaction that's not actually authored by anyone. It's a special Polkadot inherent transaction which contains the messages and some other data about Polkadot. And crucially, this data is omitted from the block that we send to the block data that we send to the validation function because it can be re-derived from the inputs to the validation function. That's already a parameter, so it would be completely redundant to pass it again. So what you're actually passing to the validation function as block data is the transactions, all the tree nodes you need to execute the messages and transactions, and that's it. So none of the messages, none of that other stuff, because it's already a parameter to that function. Right, so the other way that parachains differ from sovereign substrate is chain synchronization. So what we do is we're following the relay chain. We have information from our embedded light node about what's been finalized, what block hash. In the Polkadot relay chain's state, we can find out what's the latest block header that's been finalized from each parachain. So if we're following parachain X, we can get the latest finalized block of Polkadot. We can look in that block's state and we can see, oh, this header was finalized. So for light clients, if you were building a Parachain light client, you'd already be done, right? You've established finality on this block hash. The problem is for full nodes. For full nodes, you want to download and execute all the transactions in all the blocks ever. So the problem is there is essentially state pruning. So you can't, if you know block 1 million with some hash is finalized on your parachain, and all you have is block 100, how do you find out what's the canonical hash of block 100 when nodes on the Polkadot relay chain have actually pruned out their state? So first of all, you would have to do some kind of binary search probably. You'd have to do something clever to actually figure out which parachain block number corresponds to which relay chain block number. And second of all, even if you do that, there's a chance that that data just isn't available on the network anymore. So you could just download in reverse, right? Because you have a finalized block hash, why not just download all the blocks in reverse and then import them once you've done that? So that does work. You could do a headers only sync first, then download block bodies. But this is a bit more inefficient because when you've got a chain that spans hundreds of thousands of blocks or millions of blocks, that is still quite a lot of work to do before you actually begin executing transactions and really synchronizing with the state of the network. So the way that we do this is, so finding the canonical hash of an older header is not easy. The solution to this that we are employing in Cumulus right now is log2 ancestors. The idea is that, so log2 is basically all powers of 2, right? So you store this table with like 20 entries or 30 entries, and this is in every single parachain block's state. It's not in the block bodies, it's in the state. And then this, for each ith entry, like the 0th entry, the 1th entry, the 2nd entry, the 3rd entry, you store the canonical parachain block hash of the last block whose number mod 2 to the I was equal to 0. So this lets you do, basically you can always update this very easily as long as you have the parent hash in the block that you're actually building, because you can just see, okay, how many tables of entries of the table does this last parent hash overwrite? So it's easy to update, and it does often let you skip back very far. So you can string together pretty good compact proofs of ancestry using this technique. with an exception to the state pruning rule. So it does mean that nodes keep around a little bit more data. It's really almost nothing, but you do need to encode this special exception to the state pruning rule that allows you to essentially figure out what the canonical block hashes were every few thousand blocks in the parachain. So what you do then is you just sync forward blindly, but in the meantime you're figuring out what these canonical block hashes were at various intervals, and then as you encounter the blocks that you've downloaded at those block heights, you make sure that they actually are canonical, and you filter your peer set accordingly. So you can be like eclipsed for a tiny bit of time, and then you just kick those guys out, so it's completely fine. So just as an example of what this table might look like, I've done sort of a tweaked bit of the table. Normally it would go like 1, 2, 3, 4, 5, 6, and all in sequential order, but I skipped some of the entries because they just weren't interesting. But if like the last block number was 1,123,000, you would have these tables, these entries in the table. So the 16th entry of the table, we would have number 983,040. And for the 18th entry of the table, we would have 788,432. And we could see what these canonical block hashes were for the parachain. So we can easily just skip back to those blocks and do another few jumps and then figure out what was happening in really ancient history. So the synchronization strategy is essentially as I described. So essentially, I mean, this diagram looks a lot similar to the last one. The reason being that you're combining pieces of information from the chain, the parachain, and from the relay chain. So you're following the last finalized parachain head. You're using log2 ancestors in the parachain state, and you're downloading all blocks for the parachain sequentially, and then combining these three pieces of information in the middle, seeing what checks out, rejecting what doesn't, and you can sync successfully using that strategy. So I only have about 45 seconds left, so let's tie it all together. So just to sum it up, what Cumulus gives you is a consensus and chain synchronization algorithm that you don't have to implement yourself that lets you turn your substrate chain into a parachain without having to worry about those things. So we'll do the engineering and implementation and testing of that in Cumulus, and it will be generalized essentially to all substrate chains that embed Cumulus in their runtime as well. It gives you a collator node, which is using this consensus and synchronization algorithm to sync up to the head of the chain, and then continue to extend it with new parachain blocks. Again, you don't have to write this either. And it gives you some tools for writing substrate runtimes that know how to handle incoming messages and to send them out as well. And those APIs are super, super simple, so it's not even necessary to discuss them here. So how to get started with Cumulus? So the truth is, right now, you can't, because we just started writing it. We've just designed basically it out. But the way that it's intended to work is that, you know, it's a minimal modification of whatever substrate chain you've already written. So if you would have a desire to write a parachain on substrate, you can just start writing that chain's runtime and logic in substrate already. And then Cumulus, as it's ready, can be used to port it over with basically no effort. So that about sums it up. Thank you very much. We do have time for a question or two. Yes, you in the back. Okay.
I'll just give you the mic.
Jack's going to bring you a microphone.
Sorry about that. Can you? So I was saying you were speaking about your parachains versus sovereign chain substrates, and how consensus decision making come from relay chains. In my head, I'm trying to visualize this, but doesn't this increase like potential latency when you're doing a view change with PBFT?
Okay, so if I understand the question, it's the fact that you're following finality of the relay chain may increase latency.
Yep.
Yeah, so that is true. Essentially, you have to go through this extra step of build the block, submit it for inclusion in Polkadot, and then see how long it takes for that Polkadot block to be finalized. That's true. The fact is, though, that we've done quite a lot of work on the Polkadot consensus algorithm just to make sure that blocks can be finalized as soon as they are actually readily available. So the Grandpa consensus paper is super cool. You should check it out. Alistair Stewart from the research team did an awesome job on that. So essentially, latency is still more or less just bounded on the propagation time. As long as you're not experiencing some kind of major adversarial attack, the blocks are going to propagate out to all the Grandpa consensus nodes, and then as soon as 2/3 of them all have that block in their chain, it'll be finalized just like that.
Other questions?
Thanks. To add to that point, basically, if I got it correctly, practically doesn't have to delay the parachain advancement, because you basically submit checkpoints every n blocks to the Polkadot, or you submit or you need to finalize every block on the relay chain.
Yeah, you can do both ways. It really depends on how the block times line up. So one thing that would be quite cool is like very, very fast chains on Substrate, right, that are happening with blocks once every 100 milliseconds or 50 milliseconds or something. What we're looking at for the Polkadot block time is more in the range of like 15 to 30 seconds. So if your block time is much slower than that on your Substrate chain, if it could be 5 minutes, then obviously you would probably just submit every single block. If you have a much faster chain, or even if you just don't want to pin yourself to the relay chain that much, you can intersperse it. It's really flexible as long as your validation function can support that. But that's actually a good ticket for Cumulus. This talk has really just been focused on the idea that you would send all the blocks over to Polkadot relay chain. You don't have to do that. Yeah. Yeah.
Other questions for Rob? Okay, great.
Thank you.
All right, we're taking a 30-minute break here at this track to get lunch and so forth. So you can come back here around 1:30 and we'll get started. Thanks for coming.